In this video, we show how artificial intelligence helps us in identifying problems and performance degradations on the basis of data trends. This issue, typically known as anomaly detection, is becoming more and more important with the progressive softwarization of telecommunications. The dashboard shows LTE traffic in Veneto region. Represented data are not live, but are real data that a proper simulator streams at increased speed. The simulator feeds 3 anomaly detection algorithms. The original one without artificial intelligence contribution, the algorithm that is currently working in fields that exploits some basic artificial intelligence techniques, and finally, the algorithm that we just started trialing that is based on a multi-level neural network, what is generally called deep learning, that represents the current age of artificial intelligence. Let's focus on the upper chart. The red line represents the traffic, and we can see the typical daily trend with the traffic that drops down in the night and rises up again in the morning. The white line represents the value that we expect for the traffic on the basis of its previous weeks, the so-called profile. If the red curve falls below the white one more than a given threshold, the algorithm raises an alarm. Let's start the simulator. We see that on the 29th of September, we had a sudden drop of the traffic. This is clearly a symptom of a problem, and all 3 algorithms promptly identify it. Unfortunately, things are rarely so simple. Actually, the point is not to consider as anomalies all those situations where the traffic displaces from its normal trend due to physiological factors, and such displacements are therefore not indicative of problems. There are many cases where that happens. In this demo, we focus on one that is quite easy to understand, what we call the holidays problem. During holidays, and we are showing the Christmas week where this phenomenon is particularly evident, people wake up later, and therefore the red curve rises later than expected. Due to the steep slope, however, we get quite a large displacement with respect to the white curve, and the original algorithm erroneously raises an alarm. The algorithm called robust exponential time smoothing that has recently been deployed in fields exploits a relatively simple artificial intelligence technique to adapt the threshold used to compare the traffic and its expected value depending on the variability of the traffic itself. As can be seen, the tolerance range, represented in gray, is not fixed but widens and shrinks depending on the normal variability of the traffic, represented by the yellow line. To further improve things, we recently started a trial with a new algorithm that adds to the threshold auto-adaptation mechanism seen before a sharper prediction of the traffic expected value. In fact, instead of just building it as a weighted mean of the samples we got in previous weeks, this new algorithm uses a multi-level neural network called WaveNet, originally built by Google for the synthesis of audio signals and properly adapted by our data scientists to this specific case. We see that the red curve in this case is sensibly closer to the white one. Finally, it is important to note that this neural network is a mathematical model inspired by the structure of human brain, and therefore is able to learn from the past. As a consequence, the performances of this algorithm can improve in time.